Okay, everyone, I really apologize for that. We were having trouble with our GoToWebinar webinar platform, and hopefully we have resolved the issue that we were encountering. So with that, I'm going to go ahead and start our webinar. David, I think I'm going to have you advance the slides for me. So let me just go ahead and get started. Hi, I'm Nancy Molenda. I'm Communications Manager for the Aluminum Extruders Council, and welcome to our third webinar in the Aluminum Extrusion Tech Series. You can go to the next slide there. It's called Alloys and Temper in 6000 Aluminum Series Alloys, Achieving Properties for Structural Extrusions, presented by David Jenista of Granco Clark Inc. David, are you having trouble with the slide?
I had you enabled. I've just disabled you.
Okay, great. Okay, and David is a regular presenter at AEC member workshops and is the author of 10 papers presented at the Aluminum Extrusion Technology Seminar, the industry's premier technical conference. His key area of expertise is the heating and cooling of aluminum ingot and profiles. So on our next slide, we've got a little bit about us. AEC is an international trade association dedicated to providing information and education about aluminum extrusion and its processes. And Granco Clark is an aluminum extrusion equipment supplier based in Belding, Michigan. And the company supplies aluminum extruders with equipment such as billet and log furnaces, billet thawing systems, quenching and cooling systems, stretchers, pullers, profile handling systems, and much more. Next slide. This course has been registered with the American Institute of Architects for Continuing Professional Education. Credits earned on completion of this course will be reported to AIA CES for AIA members. Next slide. By the end of this presentation, attendees will be prepared to discuss structural and dimensional requirements with their extrusion suppliers, understand the multiple causes of poor mechanical properties, be able to define the root cause of profile distortion, defining the root cause drives optimal corrective actions, and be able to differentiate the time-temperature phase for distortion from time-temperature phase for mechanical properties. Before we begin, I have a couple of reminders. All computer and audio telephone lines are muted. So if you have a question during the webinar, please select Q&A or chat from the toolbar. Type your question in the dialog box, and our presenter will address your question at the end of the presentation. We are recording this presentation and will send a link once it's posted. Also, the slides for today's webinar are available now to download on your attendee panel. Following our webinar, we will send you an email with a link to a survey about today's presentation. Be kind, please. We ask that you take a moment to answer the brief survey. We value your opinions and feedback. Now, it brings me pleasure to finally turn over the presentation to our speaker for today's webinar, David Jenista. David, go ahead and take it away.
Thank you, Nancy. Welcome to this presentation on achieving structural properties. I know there's a wide range in the audience today. My goal is to hopefully communicate at a level that everyone will be able to follow along, but also provide some technical expertise to those of you who are applications engineers or who are more involved in writing specifications and those kinds of areas. The presentation is titled Structural Alloys. What do we mean by structural alloys? Structural 6000 alloys are the higher strength alloys. We most commonly think of 6061 and 6082, but 6005 is also sometimes considered a structural alloy, and there are some other minor ones like 6351 as well. The term structural alloy is really a bit arbitrary. For instance, if your application requirements can be met by an extrusion that's produced in 6063, if it has adequate properties, then 6063 is a perfectly acceptable alloy in a quote-unquote structural environment. But normally we're looking at a light weighting situation, and so we're looking for the thinnest walls possible, and that is, so generally you're looking for the highest strength alloy so that you can minimize the structural weight. So what are temper specifications? Temper specifications specify a processing regimen and then with it the associated properties. You can go on MatWeb and look up 6061 T6 and it will tell you what the minimum yield strength is, what the ultimate strength is, and those kinds of features. The first two letters are the general category, and then additional numbers in the sequence are more specific processing. So let's look at those. T0 is fully annealed. As the product exits the quench, the profile, it will be in a T0 state. It will have no grain structure, and it should be fully solutionized and not have any precipitates. T4 is the specification for natural aging. The 6000 series of alloys, if left at room temperature, will harden naturally over time and will reach T4 properties. It will be over an extended period of time. It's not very practical for commercial applications, so you very seldom see this specification used. T5 is the specification for artificially aged product. Coming off of the press line, the lineals are put in an aging oven, commonly at about 360 Fahrenheit, and held there for a number of hours, and the properties would be T5. T6 is the specification for solution heat treat. That, in all alloys except 6000, that requires a secondary step for solution heat treat. With the 6000 series of alloys, T6 becomes a properties specification. The values for strength and hardness are higher than for T5, and there's an implied method of processing. T6 means solution heat treat, but in the ASTM specification there's what's called footnote 9, which says 6000 series does not require solution heat treat. So the processing method is not mandatory with 6000 series alloys. What this means is that you may do your quench process in line at the press exit. And in fact, because of all the savings in labor and handling, the vast majority of 6000, essentially all of them, when you purchase a 6000 series alloy in T6, will have been through a press quench process. So it's implied solution heat treat, but really it comes back to a property specification. Are you making tensile? Are you making hardness? And so on. We're going to be talking about this press quench process and focusing most of our time on it. But I'm always careful to take a step back and note that it is not only the press quench that defines properties. And in fact, you can fail properties at 5 different stages. Let's look quickly at 1, 2, 3, and 5, and then we'll come back and focus on profile quenching. The first is the processing of the ingot, billet or log. The structural alloys are very sensitive to precipitation, growth of mag silicide, again, we're going to get into that in a minute, between 600F and 800F. And if you have reason in your heating equipment to hold a log in that range for some period of time, you will develop large enough precipitates that you will not be able to resolutionize as you go through the press, and it will lead to product failures. The intent with the structural alloys is to return all magnesium and silicon into solution as the metal flows over the bearing surfaces in the press, and specifically in the die inside the press. You have tremendous heat from deformation as you're going through the bearing surfaces, and that normally will return the magnesium and silicon back into solution. We have minimum temperatures to achieve that. They're different for each alloy. 6061, a very common structural alloy, is 1010 Fahrenheit. The problem is that there's no good way to measure that temperature because the profile is touching all the bearing surfaces as it flows through. There's no external observation point. You can't put a port on the side of it and look in because the bearing surfaces are forming the part. So what is used commonly by your suppliers is the exit temperature from the press. So we observe the temperature as the material comes out of the press, and from that we draw the inference as to the temperature that it went across the bearing surfaces. And very commonly used for 6061 is 950 Fahrenheit. We're looking for an exit from the press above 950 to assure that we got the 1010 back in over the bearing surfaces in the die. Quench practice we're going to focus on extensively, but we will come back to these three primary factors. There's a minimum temperature into the quench. It has to come in hot. There's a maximum temperature out of the quench. It has to come out colder than a temperature. And we need a specified cooling rate between the two. And again, we'll come back to this. Then, once the lineals are extruded and cut into mill lengths, they're run through an artificial age practice. Artificial age is required to meet T5 or T6 properties. Age practice fails by either overaging or by underaging. So there's a specified window that has to be met. And finally, floor age or delay between the time a lineal is extruded and when it goes into the age oven will impact properties. And this is especially true of the alloys with excess magnesium like 6061 and 6351. So we've looked at the other four in overview. And again, just as a reminder, every step has to be done properly. There is no effective remediation, okay? If I don't get the extrusion temperatures right, I can't at the age oven fix the problem. If I don't get the quenching right, I can't at the age oven remediate in some way. Every step needs to be done correctly. The first and most important concept in press quenching of 6000 series alloys, which is very different than if you're coming, say, from the steel industry, is that quenching is a preventative process. It is not an active process. It does not give you properties. It prevents the growth of undesirable characteristics. And that sort of turns it on its head if you've done anything around quenching with steel, because quenching here is a purely preventative process. It accomplishes nothing, literally. accomplishes nothing. But if you don't have it, you'll get something you don't want. The strength of 6000 series alloys comes from the primary alloying materials of magnesium and silicon. Magnesium and silicon combine to make mag silicide or Mg2Si. You'll hear it. I'll typically call it mag silicide. And this is the alloying material that provides the strength in 6000 series alloys. Meeting properties requires fine mag silicide precipitates well distributed throughout the profile. And the best illustration I have of this is sand versus boulders. What we want is we want a profile that is full of mag silicide sand but doesn't have any mag silicide boulders in it. You could compare this to cement. Portland cement, like raw aluminum, is not particularly useful. You can sort of almost grout with it, but it's not particularly useful. You put aggregate in it to make it stronger. But if you were pouring a 4-inch driveway and you threw a bunch of 3 to 4 inch diameter stones in the mix, you would have a real problem. You would have holes, you would have cracks, all kinds of problems. You need aggregate, but it has to be a lot finer. The same here. We're looking for very fine particles evenly distributed throughout the product. If you have large chunks, that's a technical term, large chunks of mag silicide, they do two things. First, they rob mag silicide from the surrounding aluminum, which weakens it, and then they form a stress riser, so it's a place for the crack to propagate. So large precipitates are not desirable. Where we grow the fine precipitates, the sand, is in a controlled manner in the age oven and not at the press line. So the goal of our quench is to not, ideally, to have zero precipitates at the press line and do all the work in the age oven. Now, as a practical standpoint, obviously, we can't do things instantaneously, so there are some precipitates, but we very much want to minimize precipitates on the press line. So how do we minimize precipitates on the press line? We have a roadmap. Our industry uses a roadmap called the C-curve, or the C-curve graph. Let's zoom in on this and take a look at it. Every alloy has its own C-curve, and we see two of them in this C-curve chart, because this particular chart that I got courtesy of Rio Tinto, which is the current name for Alcan aluminum, contrasts 6063 alloy in the pale curve and 6061 in the shaded curve. Important things about a C-curve: on the left side you see the temperature scale, and it is linear. On the bottom, you see the time scale, and it is logarithmic. And that's important to note because the 63 and the 61 graphs, for instance, don't look all that different. But if you look at the nose, the point of the C-curve right out here, the 6063 represents 3 minutes, and the 6061 represents 40 seconds. These regions, these bounded regions, are where you will have unacceptable grain growth, or I'm sorry, precipitation. Unacceptable precipitation. If you hold a 6061 lineal at 650 degrees for 40 seconds, you're done. That profile will not make properties. You will have grown too many stones and boulders, and again, it's not remediatable from practicals in a practical way. This graph shows very well. I will go to the next slide for that. from here we see our three key characteristics. We need to enter the quench well before we reach the peak of the C-curve, the leftwardmost point. And that commonly for an alloy like 6061, we're looking to be above 900 Fahrenheit. Your customer might specify 920 or something similar, but we're looking for something in excess of 900. We then see the rate. We need to reduce the temperature rapidly enough that we don't fall into the C-curve, the shaded area. And then we have a minimum temperature, the temperature out, which needs to be above or below 400 Fahrenheit. Again, in discussions with your customers, they may say, well, but we want it a lot colder than that coming out of the quench. And the reason is all of the lineal needs to be below, needs to have made rate to below 400 degrees. For a thick shape, if you're cooling only the outside in a water quench, the interior could be much hotter. So your customer might say, I want it to be 175 or 200 degrees coming out on the outside, which I can measure, to make certain that the inside is below 400. So that's, if you hear other numbers, that's the reason. Also, if you have internal ribs that can't be water quenched because they're forming hollows inside the profile, those walls cannot be reached for quenching. Only the conduction of the heat through the aluminum cools them. Again, another reason why the temperature out specification may be different in your customer. So those are our three specifications: temp in, rate, temp out. You're going to hear that a lot from me. 4 properties with quenching: faster is better. There are minimum specifications. In that case, the 61 curve, they were specifying 20 degrees per second or 1200 degrees per minute as the cooling rate, but faster is better. The fewer, the less the precipitation, the better the properties will be coming out of the age oven. So faster is better. Let's leave theory here and talk a little bit about quench units. There's lots of ways to cool profiles, and I have them here in performance order. It starts with free air. A 6063 alloy, that's what we sometimes call an architectural alloy, not a structural alloy. As we said before, if it meets your specifications, you can use it. For up to about a 3/16 inch wall thickness, will meet T5 properties in free air. Just extrude it, leave it out on the table. It's going to make properties. As the walls get thicker, you may need to add some air, some forced air cooling, but free air can get the job done for thin wall architectural alloys. As we move down, then we get to forced air. Forced air is very useful. You can do a lot of cooling. The performance metric is velocity at the part. You can compare 2 air cooling systems if you can determine the velocity at the part in each one. If the velocity at the part is 5,000 feet a minute on this one and 6,000 feet a minute on that one, the 6,000 feet a minute is going to cool more than the 5,000 feet. There's a couple of key formulas that I listed there. Cooling rate is velocity to the 0.7 power. But horsepower is velocity cubed. And noise is velocity to the 0.4. At some point, these turn into whistles. What these numbers do is they give us a practical maximum of forced air of about 10,000 feet per minute. If you're running much faster than that, your horsepower gets crazy, the nozzles get very noisy, lots of problems. And to illustrate where these numbers end up, if you double the velocity down at the bottom of the slide, it will require, to double the velocity, requires 8 times the horsepower, and your cooling increases 62%. So you don't even get a doubling of cooling rate for 8 times the power. So at some point, you know, multi-hundred horsepower fans, it just gets crazy. So we need to move beyond forced air. Forced air typically can only work for the very thinnest of structural profiles. 6005, I have some customers who are making properties with forced air with 6005, but as soon as you get to 6061 or 6082, you're looking at doing something beyond forced air. We have incorporated in some of our units an ultrafine mist system. The ultrafine mist uses nozzles that create very fine droplets, and the primary heat removal is actually the vaporization of the droplets. If you calculate the temperature of the mist, you're going, it shouldn't be able to do that. But what's happening is you're actually flashing off the droplets and creating cooling rates approaching that of a traditional water spray. We did that to span the gap from the maximum air cooling and the minimum water cooling, because there's a big gap between those two, and that can be partially filled with an ultrafine mist subsystem. The next step then is water spray. These would be larger nozzles, and this would look more like a traditional spray that you would think of, hundreds of gallons per minute. With the spray nozzles, you have the ability to adjust cooling rate. You can adjust the flow, adjust the volume, select which nozzles are on and off, which gives you ability to direct the spray and have some controllability. Moving up from spray is the flood quench. This comes in the water wall style, where the profile flows into and out of a standing wave of water, and also the dip quench, where the entire profile is dipped in a trough located typically next to the lead out. So the profile, after it's produced, is dipped in its entirety into the trough and removed. Flood quenches have quite a good average heat transfer rate. Their big limitation, and the reason why they have fallen out of favor in the industry, is there is no control of cooling rate or anything else. You put it in the water, it comes out. What you get is what you get. And you have no adjustability. So while they cool quite well, if you're wrestling with geometry, distortion, and such things, you really don't have any tools to address them. Finally, the highest performance system is high pressure or high impact velocity spray. Here, the water droplets are accelerated fast enough that they affect the steam barrier that forms around the part and provide the maximum heat transfer rate that's available. In our case, we share the same nozzle array as our standard spray. So we can give you a normal water spray and a high pressure spray with a single set of nozzles just by changing the pressure. But by knocking down the steam barrier or allowing the steam barrier to reform, you have some very significantly different performance characteristics. So it really is like having two completely different modes or medias, even though it's the same nozzle. Again, you have directable spray. You can select the pressure, you can select the direction, you can turn off nozzles entirely, so you have some control. Those are the typical design options for press quenches. So how do we assure properties at the press quench? The three properties we talked about before: temp in, rate, and temp out. Quench rate, entry temperature, exit temperature. Every alloy has a critical quench rate. Here we see a list. 6061 is probably the most common structural alloy, although automotive is using a lot of 6082 now. And we see 20 degrees a second, even 40 degrees a second. Each alloy has its own requirements. There are some new extrusion alloys coming out that have even higher requirements. We're seeing requirements in excess of 100 degrees per second with certain specialty alloys. As before, faster is better. Our targeted quench rate is typically double the critical rate because we don't want to get anywhere near the point of the C-curve. When we get near the C-curve, we're threatening our final mechanical properties. So, what is my rate? One of the challenges of measuring rate is that the profile approaches water temperature as it approaches the exit of the quench. Here you see 4 different points on a profile, one an interior web, and then near the web, and then away from the web. And you see we're getting different cooling rates, and yet they all then merge at water temperature. And the entire profile comes out at water temperature. So I don't really have a tool. I have no measurement for rate when the profile is coming out cold. What I have to do is either extrude faster, or if I have a multi-zone quench, turn off some zones and have the profiles coming out hot before I can establish a rate. My recommendation, one way to define rates is to create an alloy table. This is specific to one particular press line, one particular quench, because the performance of that quench will dictate the chart. But we can experimentally lay out an alloy table by wall thickness and time, and then the operators can use that as the assurance tool. If you're meeting the wall thickness and time specifications, you will assure your product performance at the quench. Alloy table might look like this. This is an illustration only. It's not intended to portray the actual performance of any particular quench. But in this case, this quench, if I run a 62 thousandths wall, I will cross the entire critical temperature range in 2 seconds. On a 125 wall, it takes 4 seconds. On a 250 wall, I'm up to 8. On a ½ inch, 17 seconds. 1 inch, 36 seconds. The chart doesn't go any further, because if this is an 1.5 inch or a 2 inch wall, it's more than the time required to make rate. It's probably going to be about a 3/4 inch wall. It's probably going to be about a minute, and that's too slow a rate at 1200 degrees per second. Obviously, we only have about 45 or 50 seconds to get the job done. So an operator can look at this and say, okay, I can't, or the sales department for that matter, says, okay, I can't run anything heavier than a 1 inch wall on this press and make properties in 6061. The alloy table also provides speed information. How fast can I run this? Well, if I'm running a half-inch wall, I need to spend 17 seconds inside the quench. If I'm running so fast that I'm only spending 12 seconds inside the quench, it's going to come out hot. Now, I can also verify that. I can verify the temperature in with either a contact thermocouple probe or with an infrared probe, and I can measure temperature in and measure temperature out. But that information is also contained in the alloy table. I have to run at a speed where I am spending 17 seconds inside the quench if I'm running a half-inch wall to assure properties. So I like the alloy table. It's simple. It's something that can be used throughout the organization, and gives us a clear definition of what we can do, and more specifically, what we can't do. Again, a review on quench performance. I've seen this before. Make rate. Make temperature in, that's a minimum, and then make temperature out, that's a maximum. Earlier I said that for properties, faster is better. But what happens if I have interesting profiles? What happens if I have a flatness specification, a squareness specification, a contour issue where I have two contours that have to slide one inside the other, or if I have a critical gap clearance? If I cool rapidly, I run the threat of distorting the geometry permanently. How do you do permanent profile distortion? Permanent geometry distortion occurs when, at an instant in time, the mechanical stress induced by the quench exceeds the yield temperature, the yield strength of the material at the current temperature. Now, the white words are important. Our cooling rate affects how much mechanical stress is applied, but the yield strength is at the current temperature. When the metal is hot coming out of the press, the yield strength is a couple of orders of magnitude lower than it is after it's been aged and is sent to the customer. So you can look it up in a data book and say, oh, this has 35 KSI yield strength. That's true for a fully processed shape, but you have a tiny fraction of that yield strength when the metal is hot coming out of the die. And this is where we end up facing challenges with geometry. I tell customers regularly, say, well, I want to be able to do everything with this quench. And I say, if you let me design the die, I can design a die you cannot quench. I've been around it long enough that I know some of the characteristics of what's challenging, and I can make a challenge you can't fix. But there are tools available here. There are tools available for us to handle profile distortion while still making properties. The importance of delta T, the temperature difference between the profile and the water, is a key to this understanding. Your cooling rate is delta T times your cooling mode, whatever that mode is. So let's just take an average cooling rate of 20 F per second. If we're averaging that across the quench, that means when the metal first comes in and it's at 950, we're cooling it at about 80 degrees per second. And at the back end of the quench, as it's cooled off, we're cooling it at something less than 10 degrees per second. So the challenge in quenching is when the metal is at its softest, in this illustration, we are applying 4 times the recommended cooling rate. So that is the primary cause of distortion. We see the illustration here. If we are averaging 20 degrees per second, then we have a single zone quench where it's only one media throughout the quench, one cooling rate. We're getting excessive cooling at the entry, and we're actually getting inadequate cooling at the exit. The solution is progressive quenching. This involves using a quench with multiple zones and adjusting the performance of each zone. If the specification is 20 degrees per second, in theory, what we'd like to do is have about 20 degrees per second in zone 1. We'd like to have about 20 degrees per second in zone 2, and we'd like to have about 20 degrees per second in zone 3. Actually, the biggest challenge in this is zone 3, because our delta T has gotten so low, it will be hardest to get 20 in the exit zone. But we can easily turn down zone 1 and zone 2, so our average temperature is actually our sequential temperature. And this is the tool that allows the making of mechanical properties and the maintenance of the profile geometry. We see that as we look at the C-curve, that critical temperature range where we want to pass as quickly as possible is from something around in the low 800s to something in the upper 600s. This is the supercritical range. This is the range where we want to rapidly transition this zone. What that leaves us is the area above that. In this area, we can be a little more gentle and still make properties. So our entry zone is the place where we can manage any geometry issues. Again, from a property standpoint, faster is better. If you have a solid rod you're running through this quench, run all the quench you can. Fine. But when you struggle with geometry problems, you go to the entry zone of the quench and you turn down the performance of the entry zone in order to minimize the deformation of the geometry. What I like best about this as a factory process guy is the tools that it provides to the operator. In the old days, and I'm old enough to remember the old days, what we told operators was you need to cool it fast enough to make properties, but not so fast that you distort it. Which is kind of like telling a pitcher, don't give him anything he can hit, but don't walk him. Okay, and it really was sort of a cognitive dissonance thing for the operators. With the progressive quenching approach, you can very easily teach operators what to do. You address distortion issues in the entry zone of the quench. You address the properties issues downstream. If you're not making properties, you increase the cooling rate in the downstream zones first. And only then do you begin to increase the cooling rate in the entry zone. By contrast, if you are struggling with a geometry issue, you only go to zone 1 of the quench and turn down the cooling rate there. You don't turn down the rest of the quench because, again, that's where you have the highest delta T, the highest cooling rate will occur as the profile enters the quench. and it is also where the metal is the softest because it's hottest. So to summarize our discussion today, if we face issues with properties or geometry with a structural alloy, we want to verify the entire process. Do not assume it is a quench problem. We need to make certain the entire process is in control. We need to verify that the temperature into the quench is high enough. We need to evaluate the quench rate. We need to make certain that the temperature out of the quench is low enough. And we need to deal with any issues of geometry distortion at the entry to the quench. That concludes our webinar, structured portion of our webinar. And I'm looking forward to any questions that we may have, and I'm going to turn it over to Nancy as our moderator.
Okay, thank you, David, for a great presentation. We do have time for a few questions. So as a reminder, if you have a question, select Q&A or chat from the toolbar and type your question in the dialog box. So I'm looking through and I'm not seeing any questions just yet. Does anybody have any questions about what David presented today? While we are waiting for questions, I want to thank everyone for their patience and understanding during our technical difficulties. I assure you, this is not normal. We don't normally have these issues, so thank you for being so patient. Okay. All right, we've got a question from Jonathan who is asking, you stated 6063 could be a structural application. Could you explain why this is different than 6061?
6061 has about 3 times the, not quite, 2 plus times the yield strength of 63. So 6061 can have a thinner wall in the same application. That means you're using less material and you have a lighter part. But 6063 is much easier for the extruder to process, and it extrudes much more quickly. If you want to look at cost, you basically look at the raw material, the aluminum ingot, and then the press time that's used to extrude it. And every one of your extruder suppliers has their own number for what that press time is, but and that covers all the overhead and everything. But they say so many dollars an hour for press time plus the cost of the material, and that's their cost to you. If you make a higher strength alloy, it will typically take more press time for the same lineal, but it will use less raw material. So that is a trade-off. But yes, if you can meet the requirements of your application in 6063, say 6063 T5, then you may certainly utilize that in your application.
Okay, great. Next question we have is, how can we control spring back after T4?
Spring back is a characteristic that can be affected by both press parameters and by age practice. I cannot give you a simple, here's what you do to control, to improve spring back or to minimize spring back, but it is very closely related to how much precipitation has occurred.
Okay, and the next question we have is, in the presentation, you listed cooling rate in Fahrenheit per second, but spoke as Celsius per second. I'm assuming that the cooling rate numbers will be different in Fahrenheit per second versus Celsius per second.
I did not intend to use Celsius. If I use Celsius in this presentation, I was mistaken. Obviously, and you can download the handout and you can look at those, but every rate shown in Fahrenheit, you would divide by 1.8, and that would be the equivalent rate in degrees C. I work in both, and for this presentation, I thought most of the participants would be more familiar with English units. So I intended to be consistent about that, and if I said degrees C, I think I misspoke.
Okay, thanks. What will be the optimum time to move from homogenizing furnace to cooler? What parameter to be considered to decide the moving time? Does that make sense?
It makes sense, but I am not an expert in the processing of ingot, billet, and log. I know that it is a contributing factor and it needs to be controlled in the process, but the specifics of processing I just simply can't help you with, and I apologize for that.
Okay. This person followed up with alloy 6061, homo temperature 1040. I don't know if that helps at all.
Granco Clark, in their history, has built homogenizing ovens. I'm familiar with their function, but I cannot help you with specific set points for the equipment. I just, it's not in my wheelhouse, my area of expertise.
Okay. All right. You mentioned early on that once the quench has been done incorrectly, too slow, that the properties cannot be met with practical methods. What are the less practical options? The specific case in question is a short-run prototype where the prototype supplier determined they could not properly cool the lineal out of the press.
A solution heat treat cycle followed by artificial age could restore that. A solution heat treat cell would be typically a vertical oven with typically a glycol bath underneath it. And you raise the profile into the oven, heat it back above solvus, meaning putting all of the mag silicide back in solution. And then you rapidly plunge it into the quench media. That should give you, theoretically, as you pull it out of the quench media, a T0 part. And then you could artificially age that on the appropriate time. So yes, that could be done. It is very unlikely that the supplier in this customer's case has that equipment on premises. There's only, I would be surprised if there's 20 or 25 solution heat treat facilities in North America.
Okay. Our next question is, could you explain a bit more on Note 9, where the condition T4 can be obtained at the press, while theory says that a quench from an elevated temperature process gives a T1?
Well, T5 and T6 both require artificial age. So you cannot achieve T5 or T6 at the exit of a quench. But
did I say 5? It said T4.
Yeah, and the common specifications when you purchase 6000 series profiles will be a T5 or a T6. That's as purchased. That's not as it exits the quench. As it exits the quench, yes, in theory, it's a T0/T1. It then requires artificial age to reach either T5 or T6. If you don't put it in an artificial age environment, it will, over a period of weeks, reach T4, but you will not be able to make T5 or T6 properties without the artificial age step. And what I may have said is that it's possible to get to T6, or I intended to say it's possible to get to T6 using press quench. Not that it is T6 as it exits the quench. And if I said that, I misspoke.
Okay. Is there a rule of thumb as to how much the temperature increases during extrusion as a function of alloy extrusion ratio and extrusion rate? Yes,
those three come together, and I know there are simulation programs out there that simulate that process, and that's exactly what they look at. What they're looking at primarily is strain rate, but strain rate is driven by the three things you mentioned: by the profile geometry, how much you're working it, by the temperature of the material, and by the fundamental properties of that, which is to say the alloy. So yes, that can be done. It's non-trivial, if I may say that. But there are a couple of commercially available simulation software systems that actually simulate that. So it is all formulaic. It can, in fact, be determined numerically.
Okay. And then, is there a limit of time for 6061 alloy in the log furnace while holding billet temperature?
You would not want to hold between 600 and 800 for more than 10 minutes. That is the rule of thumb. Once you get above, I know the number in Celsius, above 530 C, above about 980 Fahrenheit, I think I'm doing that calculation in my head right, you begin to put the magsilicide back in solution. So actually holding at the discharge end of a furnace can actually begin the process of resolutionizing the ingot column, and is actually beneficial. Holding at 980 or 1020 for a few minutes, there's actually some work done on that. If you have access to the extrusion technology papers, the ET papers, there's been some work done on that, some good work done on that in the 1990s out of the Hydro organization.
Okay. And I think this is going to be our last question. Is there any heat treatment literature on alloy 6082?
Is there any heat treatment?
Literature?
Yes. Yes, the literature is out there. I would be very surprised if you Googled 6082 T6 if that wasn't, if you couldn't find sources. The primes have information on that. You could go to a Hydro aluminum, you could go to a Kaiser, to a Rio Tinto, and there's a lot of information there on the heat treatment of specific alloys. The rates that I used, that I showed, were all from Rio Tinto sources.
Okay. All right, well, David, thank you for a great presentation and for sharing this information with us, and thanks to Granco Clark and all of our members. You can go to the next slide, David. The recording of today's webinar will be available online soon on the AEC website, and we will send you a link once it's uploaded. And the evaluation survey for this webinar will be sent to you following this presentation. Please share your comments with us. Your input is very valuable and helpful in determining future webinars. And if you can go to the next slide. And be sure to visit our website for more information on upcoming webinars and aluminum extrusions. And the website also has information and resources on aluminum extrusion design, applications, technical information, and much more. So you'll find a lot of stuff on there that you might want to use in your extrusion design. And finally, I want to tell everybody about Extrusion Design University, or EDU18. It's a new event that was created for designers, engineers, specifiers, and others who are interested in attending an in-person educational event to learn about aluminum extrusion design and process topics. It's scheduled for May 14th through 16th in 2018 in Chicago, and it will include topics arranged in tracks covering architectural, automotive, and industrial applications of extrusions and related topics. And the event is intended to bring together industry experts like David and extrusion customers to assist attendees in honing their aluminum extrusion knowledge and design skills. And the subject that was covered in today's webinar is the type of things that you'll see at Extrusion Design University. And for more information, visit aec.org/edu18 and be sure to save the dates. And that concludes our webinar for today. Thank you for being with us and for your patience and understanding. Thanks so much.